Okay, so this is our current skin detector, and what it is doing is searching for color values which are experimentally confirmed to be corresponding to human skin. And what our program does is initially picks up from the webcams we're using in class the RGB values. That's kind of what your eye does too. The problem with this is that R, G, and B are highly correlated with respect to each other and with respect to the luminance of the image. So red is really, really bright. You take out the red, it gets a lot darker. Blue is not very bright at all. So what we're doing is translating it into a different color space, one called YCBCR, which takes as components Y, the luminance of the image, and then CB and CR, red and blue chroma. And using those, we can kind of get a better idea of what color something actually is without respect to how bright it is. So human skin values are something like from 80 to 130 CB and from 130 to 180 CR. And that's what we're picking up on Brett here. He is wearing pants. It's his tan pants, which are approximately human skin value according to our program. You'll also see that there is almost no background evident. It's all black. That is the background removal we've implemented. At the beginning of our scene, we kind of look and see what should be empty, and then he steps into the frame and it recognizes immediately that he is different from what was there before. We are using k-means clustering to identify unique skin regions. At this point, it is looking for 3 skin regions. K-means clustering works by assigning essentially random means that it thinks might work, and then every point that's closest to each mean is assigned to that mean. You take the average of the points assigned to a mean, you calculate a new mean, and then you do the same thing over again until you get 3 things which approximately divide the region. So on me, I'm wearing an orange shirt, so it detects my whole body, upper body as skin. And the points you can see kind of generally form into a triangle shape, which you would associate because there's lots of points on top and then a few towards the bottom.
So this is some work that Kate has been working on, doing background subtraction and triangulation. So what you're seeing on the screen here are 2 sample images from the data set, the left and the right image, and he's subtracted out the background and made it black. You can see we maybe even need to tone the threshold down a little bit because we lose some points in the knees and the waist area and the upper shoulder. But from this, he's also written some triangulation code that would get the disparities. Should note right now, as an optimization, we're only calculating the disparity for every 16 pixels and setting it to the same thing, which is why you get this sort of blocky pixelated regions. Eventually, we'll probably do it per pixel, but for testing right now, it's a little faster to do it this way. From that, we get the 3D point cloud, which feeds into my algorithm. The way it works right now is we'll eventually take the skin regions that Graham's code is detecting. And for each skin region, we basically grow a cluster out from there based on a bunch of heuristics about how far basically the human reaches to sort of limit the search space. And then we filter that. So right now, what you're seeing on the screen is 3 different clusters, the face, the arm, and the hand, that were just seeded by sort of simple points right now that we calculated for where they should be, and they've grown outward from there. You can see we still need to tune the parameters a little bit because eventually what we'd like is for example, the head region should actually grow the whole body down from there. Because what we really want to do is detect the skin region that corresponded to the head. So we'll go from a point cloud cluster that should hopefully be the whole body. We'll filter that out and then take that into David's pose code.
I've been working on the human pose modeling. As part of that, I've written a utility function to output the OpenCV matrices in MATLAB format so they can be visualized. I have built the human model and determined rotations that are physically reasonable to constrain the amount of poses we need to consider. When I run this, it chooses a random pose inside of the range of physically feasible poses and outputs it into a terminal window. Once that is output, I can then take that output and copy it into a MATLAB window where I can then run the draw human command that I wrote, if I can type, to display the pose that was generated so that we can make sure that we are only considering physically reasonable ones, because anything we can do to reduce the search space is a good thing. This is kind of pushing physically reasonable, but some of the joints that contribute to this unreasonable pose are in reasonable positions, so that's where we are at the moment.